anyway. Okay, so this is going to be a couple, just 3 hours of machine learning. So I had no idea how diverse was the background, so this was kind of the problem in preparing these 3 hours of slides. So just to begin with, just give me an idea, how many of you have had a machine learning course before? Okay, so for you, I mean, some of the stuff I'm going to say, quite a lot of it might be a bit introductory. The whole plan, I thought, was to give you a kind of the idea of a kit, like a set of tools that you'll be able to use, like basic tools, but these are tools that you can further develop. And so I'm going to start from basic things and try to give pointers to more sophisticated solutions. So you already had yesterday quite a bit of an introduction about machine learning. I just want to say, one way to look at machine learning is somewhat sitting in between the idea of studying intelligent systems, developing intelligent systems, intelligent solutions, and in general just making sense of data, okay? And it turns out that since a lot of approaches to develop intelligent systems are actually based on data-driven approaches, so a lot of problems you cannot just solve by a set of rules, so you need to actually look at data, an example of potential solution to the task to devise your own solution. Data and techniques to deal with data are linking these two seemingly different words. And what I want to try to do today is, again, my goal was try to introduce basic key algorithms that you can use. So I'm not going to do much theory. Kind of yesterday mostly covered most of the conceptual part I will need today. I'm just going to show you algorithms. I'm actually getting to the point where you can use them. And this afternoon there will be a lab session where you basically have all the algorithm I showed this morning implemented and you can play with it. Okay, so you can have play them with toy data, but also with some real data problem. So this is probably a superset of what I'll be able to talk about. So basically, it's divided in 3 parts. The first part is the keyword is really this idea of bias variance. This was only mildly touched upon yesterday, and it's basically, if some of you remember the whole story about regularization, fitting, smoothness, it's going to be about, okay, but how do I find the best lambda, the best parameter, the trade-off, fitting and smoothness, okay? So a key idea was that if you have to learn from data, because data can be incomplete and noisy, you actually need to impose some form of prior, but then how much you believe the data, how much you want to enforce the prior is something you have to decide. And the first part, we're going to look at very simple methods where I don't have to explain much, and then kind of deal a bit with how you actually tune the hyperparameters of your algorithm, okay? This is basic, but it's kind of the one question you always have to ask when you get an algorithm. How many hyperparameters I have to choose and how I choose them? The second part, we'll move on and actually see an instance of regularization, pretty much what you saw yesterday, but we're going to just zoom in a little bit and just see simple methods. I'm mostly going to describe Yogi Squares solutions, but I'm going to tell you how you can make linear models into non-linear models and how you can turn parametric stuff into non-parametric stuff. I'll tell you what non-parametric means in a second. And I should be able to get here. Then here we'll start to be in, depending on also how much your cursor of different things, how much we will be able to cover. The last part is really moving away from kind of black box machine learning methods into kind of asking the question, okay, which information is important in my data? What are the factors that are actually affecting my decision and my predictions, okay? So we try to actually understand a bit more, not only how to get good prediction, but what are the factors that are actually fundamental to do this, okay? The first part is going to be, I'm going to give you a glimpse into variable selections. This is sparsity. And you still have, here you still are looking at supervised learning where you have labels, and then I'm just going to briefly remind you what PCA is and give you pointers to how to make it more complicated. And this will be the only unsupervised part. And last, this afternoon, we're going to have this MATLAB session. There might be an extra hour and a half tomorrow. I'm not sure if it's confirmed. It's still maybe. Okay. So here we go. Again, so this first part, the main idea is that I want to talk about the trade-off between stability and fitting, and how you decide in some kind of principled way how you extract the best trade-off between these two principles, okay? And because I didn't want to I want to focus on this part, I'm just going to look at extremely simple methods. So the setting we're going to discuss for quite a while is that of supervised learning, okay, which is basically learning function from samples, okay? So my problem is I want to learn a function from an input to an output, which should be good for every new input I might get. And what I have at disposal is just a couple pairs of input and output. And this is my training set. This is data. Make sense? So this is the kind of problem I want to look at for quite a while. And this is just one example so that we can all have this, at least one example in mind to which we can refer to. So pretty much every camera these days has this kind of stuff that put a little circle around the face. How does it do that? I don't know the exact algorithm on the iPhone, for example, but pretty much the overall idea is you're going to get an image like this, okay? If you look close, this is color, but imagine it's just black and white, okay? Then each pixel will be a number between 0 and 256 or something. And then you can unroll. So this image will turn into a matrix like this, and then you can unroll it into a long vector, okay? Same here, this is another image. This does not contain a face. This is still a set of pixels. I will unroll this into a vector, okay? So I stuck all the images, okay, each one described by a bunch of pixels in rows in a matrix, and this is going to be my input matrix. To each of these rows, which again is just an image, I'm going to have associated a label. In this case, it's just either +1, say face, and -1, not a face, okay? So we'll see in a minute that we actually use fairly simple ideas. One thing that makes everything complicated is P. What I mean by this is N here is the number of images. P will be the number of pixels in an image, okay? And even for relatively small images, this number is pretty big. So with respect to a lot of classical statistics, machine learning is very similar to statistics in a lot of respects. One main difference to classical statistics is that the number of variables you have to deal with is extremely big. Okay, even in the simplest cases, 100 variables are just normal. Okay, and 50,000, 1,000, like a million variables or 500,000 variables is actually pretty normal. So this is kind of a new game. We'll see in a bit that it makes a lot of, it's a big difference. Okay, so this is the one example just to keep something in mind. This is you want to recognize whether an image contains a face or not. And you're given a bunch of images where there are faces and a bunch of images where there are no faces. You encode them in this naive way. Of course, this is not probably the best idea just to take the pixel, but it's a beginning. And then you just have a vector of labels. So this is your data, and now you want to be able to, given a new image, say, is there a face or not? Okay? Is this clear to everybody? All right. So because of manifest a limitation in my drawing capabilities, we're going to think of images which are made of essentially 2 pixels just to be able to do stuff, okay? So you think of each of these, say, as a face, and each of these as a non-face. And the game is going to be, okay, we want to find a rule, okay? We want to draw here a line that would divide the space in blue and orange, and then we're going to say if a point falls in one region, it's going to be, say, orange, so face, or otherwise it's going to be non-face, okay? And the first question is, suppose that I give you this one triangle here, okay? And I don't know whether it's orange or blue. What would you say?
Orange.
Why?
Cluster around other orange.
Again?
It's in a cluster of other oranges.
Yeah. Even simpler. Cluster is kind of fun. So it's in a bunch. It's immersed in a bunch of other guys, okay? Particularly, one way to check this is that if you look at the closest one, it's just an orange point, okay? This is like the simplest rule you can imagine. It's called Nearest Neighbor, okay? It's the intuitive thing that you kind of do when you do that, okay? In that case, it's so simple that you don't have doubt. All the closest ones are actually orange. As simple as it might seem, this is actually pretty nice and working in a lot of situation algorithm. Is based on this very simple intuition. The nearby point should have the same label. Okay? And there is a large class of methods, and you'll see that as simple as it is, this is actually a good building block to build more complicated solutions. So The simplest version of this is when you get a new point, compute the distance to all other points, and check the closest neighbor in the training set. So this color stuff is training set, the black one is a new point. I check what's the closest point, probably in my drawing is this guy. It's orange, so I say that this is orange, okay? For this kind of methods, actually, it's this one is still okay. Usually it's kind of a bit of a pain to write them down. So what I do is that you give me x bar is a new point. I compute the distance to all the xi's. These are the row of the matrix before, okay? So these are each of these guys an image. I check the index of the closest point, and then I assign as the label to the new point x bar, the label of the nearest point, okay? I don't care that you particularly digest most of the equation that I'm showing. Most of this stuff you'll actually see implemented, and if you can just go back to this to actually check how it's doing. This is so simple you might probably just digest it right away. Some other will not be as friendly. So what's good embedding this algorithm? Okay, how does it work? Now let's see if this can make it work. Nice. So I'm just going to build a very simple data set. So what I take is 20 points of this data set called 2 moons. A few of you may have already seen it. Okay, so this is the data set. Forget about this for a second. This is your training set, okay? 2-dimensional points. These points here are one class. These other points here are another class. These are 20 points. You can kind of see that here what I gave you is just much more points, okay? We're cheating on the set of the board for the slides, okay? Typically, this is what you have in practice. But since in my simulation I'm God, I'm actually also going to put here an enormous amount of points that would be the population from where these guys are coming from, okay? So imagination effort, these you have, these you typically don't have. It's the simulation. And so what we're going to try to do is now to see a bit how, given this data, you can find the solution and how the solution will work on new data. So these are the new data, the future data, okay? So the game is find something based on this that will work well for this. Make sense? So let's see. So I'm going to choose just nearest neighbors. This is kind of what I get, okay? So you can see, again, so what do you think? Is it a good solution or a bad solution? What is good embedding nearest neighbor? Do you like it or not? Would you use it every day to build the iPhone apps or not?
Got that an outlier orange in the bottom left that probably might be a misclassification that seems to be cutting into the way it actually works with the test.
Right, so I guess the comment is if you have a point, a single point might have quite a bit of importance, and you might pull your line all the way down here, and if you turn yourself into God just for a few seconds, you can check that you're definitely right here, because you see all the blue points that are falling in the orange region will be mistakes, okay? And the other way around. Okay, this is not so good. What's good?
It seems to get most of the test.
Right.
Each side.
I guess what I'm pointing at is essentially that if you look at this curve, you can say that it's kind of jagged, but it's also very, very, potentially very complicated, okay? So we follow every point because we gave the algorithm the power to actually do it, which is kind of good. This is the first example of a non-parametric method. You don't know exactly how to parameterize this curve, but you do know that you can build very complicated stuff, as complicated as it gets. You can follow pretty much any point, okay? So from the point of view of the stability fitting trade-off, this is definitely biased towards fitting, okay? We unleashed him to just follow any point. He can be arbitrarily complicated, but can be extremely unstable. And a comment about the outlier down here is the first example. And just to give you an idea, if I generate another data set, okay, just the same, looks very similar. But so you see? So this is another manifestation, okay? As simple as it is, this gives you a vague feeling. This is the same solution. This should be the solution to the exact same problem, okay? So what I did is I take another 20 points, and I just compute the solution. This is what I get, okay? So even more than just following this one point that was here, if I give you another sample, the solution is completely different. And this reflecting the fact that, and this actually is worse, but you cannot pick the data, okay? So remember that all this thing you have is this, and this is what's happening on the other side, okay? So even more than just looking at that one outlier, what you see here is that as soon as you start to sample the data, and here we are in 2 dimensions, okay? You will see that in high dimension things get much worse. I just give you 20 points. The way these data sets works is that I have basically this data set here and this data set here, and then I decide a certain amount of labels that I will flip. Okay, in this case was 5%. Okay, so how shall we fix this? What is the next? So nearest neighbor is the dumbest algorithm you can think of. What is the second dumbest you can think of?
Get more neighbors.
Get more neighbors. So this is it. Boom, boom, boom. This is my reminder. And this is the get the point, okay? If you start to get a point, for example, this point here, which class would you say it is?
Circle.
Circle, probably orange. It's not completely clear because now I start to get close. If I make an effort to make it close to this guy, what you kind of see here is that probably the nearest neighbor is wrong, okay? But most of the guys around him are actually orange, so you probably feel like saying it's orange. That's what your brain does looking at the picture, and so probably that's a good idea, so you can see what happens, okay? And so this algorithm is kind of a pain to write down, or at least I didn't find a particularly nice notation, but let's say in words because it's easy and it's easy to code. Take a point, compute the distance to everybody, sort them, and then take the first k neighbors, okay? We probably might want k here to be odd, so that we can make a vote, so you can have all the neighbors voting orange or blue, and majority wins, okay? So that's what you do. And this is called the K-nearest neighbor. And these are my few lines. The basic point is you take all the distances, you compute them, you rank them, you find the indices, and you take the first K, okay? Look at this quickly, don't get too confused, but the main point here is take the indices of the K nearest neighbor and take the average. Since these labels are just +1 or -1, if they're odd, I'm just taking a vote, okay? Majority wins. And I could normalize here, it doesn't really matter, okay? Okay, does this make it for us or not? Let's see. So, this is exactly the same as before, okay? I may even have it here. Okay, so this is 1 nearest neighbor. This is 5 nearest neighbors. Okay? Unsurprised, say. So you can do 11. Okay? Weird. So I start to make it more regular. Okay? It's still jagged. So this is still an extremely non-parametric estimator. Again, it's very complicated. When I say non-parametric, it means that basically parameterize this with a finite number of parameters is not easy, okay? But you do see that the solution is way more regular. And we can check, perhaps, generate another data set of this kind. It's a small data set, so it's pretty much the same. Okay. Test. It does change it still, but a bit less. Okay. Take 1. You will see that I think it's pretty crazier. Not always, okay? So this, for example, looks actually pretty good. This is the 1 nearest neighbor, and this happens to be, look at this data set, it's pretty good. Okay? For some reason, I do not have a single point here because it's just a sample. Again, I make it twice. Just don't fool yourself. I just make it twice and do the same thing. This is what I get, okay? Let's do the same thing. This guy. Is actually pretty regular, okay? So anyway, so this is just it's not rocket science. It's just to give you a feeling. So this algorithm is just an excuse for me to show you in a simple situation the simplest algorithm that somewhat manifests is control between fitting and somewhat getting something regular. Yes.
How do you plot the curve? How do you get the equation of the line?
I don't. So the question is, how do you get the black line? I don't. So what I do for this is basically that I take a uniform grid of points, dense, and I classify them. Okay? So I take +1 and -1, and then I draw the 0. I cheat. Okay? It's just one way to plot it. Okay? I definitely don't have the equation for that. Okay? Okay, but anyway, so this is just again this is just to make the point that this is the simplest algorithm for which you can see this kind of effect. I think is the first algorithm to know because it's so simple. It's like whenever you think of something fancy, okay, some important new method in the world of machine learning, you might want to try this because it takes 15 seconds to code, okay, and then you can check if you really fancy method works much better. So the algorithm can actually be made much fancier. One obvious intuition is that closer points should count more. So there are neighbors and neighbors. The closest neighbors we kind of like more than the most far away neighbors. Okay? So what this method does is it basically says you put a window around each point, and then you can basically say that furthest point should count less. And this is basically the idea behind so-called hardened windows or kernel estimators. And this is the idea. Instead of just looking at the distance, you're going to put it on top of a Gaussian, okay? And then you can control the width of the Gaussian. If you make the Gaussian very small, each point is just going to look at a very small number of neighbors. But if you make the Gaussian very big, your computer is going to be able to see everything, okay? Here, there is not the number of neighbors to parameterize the models, but there is this width of the Gaussian that basically play the same role. Okay, you could implement this, try to do the same game I did, and you will see that this sigma has exactly the same effect. If you make it very small, you basically can get like delta function over points. You can get arbitrarily complicated surfaces. But if you make very big Gaussians, basically in the end, you're just counting the number of points in your whole training set. The other thing you can do, and you can already see it from this equation, but even more clear in this case, I wrote everything thinking that my data are the one I show you. So basically they are vectors and you just use Euclidean distance. There's no reason why you should do that, okay? If you do have special kind of vectors, for example, binary strings, and you do have a distance, for example, the Hamming distance, then you can just use that, okay? The other thing you can have is more complicated similarity measures that come from your friend who's an expert on face recognition, whatever problem you're looking for, and you guys together build together a good way to measure similarities. And once you have it, you can just plug it in here. Okay? This is not an easy problem. Okay? Finding the good similarity is probably much harder than doing this. But if you have it, okay, then you can just plug it in. And so the simple nearest neighbor, k-nearest neighbor can actually be made fairly complicated. And one could keep on going instead of taking just this kind of piecewise constant approximation locally. You can do somewhat the linear interpolation locally or polynomial interpolation locally. And you can make this more and more complicated. All this for me is an excuse to look at this one remark here. You always have at least one parameter that gets you from complicated to simple solution. Okay? And there is the one obvious question, how do you choose it? Okay? Then if you're mathematically inclined, you can ask, is there actually an optimal value? Okay? Shall I just make it the bigger the better, or shall I actually choose it in a careful way? And if you're less mathematically inclined, perhaps you can ask, can I compute a good value in practice? Okay? If it exists, but I cannot compute it, maybe it's not that interesting. And so I guess this is one possible answer. Is there an optimal value? Okay. What's the optimal value of the solution? We could go back to the plot. I won't do it. Okay. I'll do it. So which one is, what's the basic idea here? Okay. If I could, okay, and a lot of people when they submit paper to conference, they actually do, you will optimize your K, not here, but here, okay? If you had a disposal data, okay, that represent the future prediction, that's what you would do. You would choose the K. Among all the possible ones we showed before, we'll choose the best here, right? Yes, we're happy if we make good prediction here, but this is what we really care about. You know, getting new, not the recognize the 5 pictures on my mobile phone, but I should be able to recognize faces for any picture I will take in the future. Okay? And so, mathematically, the way you write this down is basically saying, okay, I'm going to take yx, okay, any possible yx, not the one in my training set, but any possible pairs. I'm going to take the expectation of the prediction. In this case, I take least squares of my solution to the true one. Okay? So this is the average error on all possible xy pairs of my estimator. Okay? Okay.
What was S?
I haven't told you that, but I will. What is S? Okay? S was the training set. Okay, the set of xy pairs I have to do at the beginning. The question to you is, why do I have to put it there? What happens if I don't put this? Suppose for a minute that you have access to all the x and y, you compute this quantity, you minimize for k, and then what can you say? That you find the best k for what?
Training set.
For this guy, this one training set that you have, okay? But then you have to say, well, maybe that training set is not, you know, the only one I can get, so I can get other training set in the future. I want to be sure that this is a good choice for everybody. So the simplest thing you can do is that you can average out with respect to many training sets, okay? Tommy showed you much more complicated and fancy way of doing it, controlling not only the mean, but actually the whole distribution of this quantity. For today, I'm just going to stick to this. Okay, so I take the first expectation over all possible pairs in the future, and then another expectation over the training set I'm given to solve the problem. Make sense? So the first question, so do we all agree that this is kind of a reasonable quantity to look at? There is an obvious problem, okay? If you're not mathematically inclined before. You don't have this, you're not able to compute this expectation, you're not able to compute this expectation, okay? So whatever I'm going to say for the next 2 slides is purely theoretical, okay? And we'll answer this question. Is there an optimal value, okay? If there is, then I can try it. The basic idea here is if there is one, then I can sit down and try to be able to compute it. If there is not one, I can go home, okay? So we're going to do first a couple of computations to see that there exists one. And so we basically, I'm going to show you a bunch of equations, and I'm just going to try to point out what you should look at. The basic point is that by trying to characterizing a bit this minimization problem, does it have a solution? What's the shape of that function? How does it look like? You can view this as once you fix these 2 expectations, you can view this as a function of k. So as a function of k, how does it look like? Does it have a minimum? What does it depend on? Okay? And by looking at this problem, we kind of unveil one of the most fundamental aspects of machine learning, and more general, I would say, of approximation and estimation. Okay? So, whatever I'm going to show you now is a bunch of equations. Okay? I'm basically just going to give you a vague feeling of how you get a certain result. All the math in pretty much everything I have doesn't go beyond linear algebra. Okay? So I'm not going to prove anything, but basically every step where you see a calculation, if you're not done it before, you can just spend some time and just, it's an exercise. Okay? So there's nothing more complicated than gradients and sum of independent variables and stuff like that. Okay? It's all linear algebra and basic probability. So what I'm going to do here, basically what I want to do is to rewrite these in a few ways. And we do this by looking at a particular model for the data, which is not the classification model, it's a regression model. That is that you have a true function, and then there is some noise. So you get an xi, which is random, then you get the delta I, which is also random, and then produce yi. So this is the most standard regression model, okay? And here's my notation, this is a small I. So basically, this noise is zero mean, okay? And it has a certain variance. So just think of the one-dimensional situation, or maybe you really have to think about it. So this would be my x, this would be my y. There would be a function that is fixed, but I don't have it. I have a bunch of points, okay? This is all dreams because I don't have any of what I just did, but what I have is that you have this coordinate and this, okay? This is the y, y, x, and so on, okay? And the idea is that this noise, this point basically is most likely, I will find it there, but it will be spread out a little. So then to do this computation is much easier, it's not needed, but it's much easier to actually condition over x, and you can prove that you can interchange the expectations. Forget about that for a second. I'm basically fixing the x. The key point is that we will want to compare this guy, okay, to this function here. And to do it, we're going to introduce an intermediate object, which is still theoretical. It's not this and it's not this, but it's something in between. What is it? Is the average at each point of this guy. So it's a theoretical object because you're going to have this, okay? Remember that this fk was just the sum of the yi, okay? So if you take the expectation of yi, it comes here, this the expectation of this is 0, and so all you get is the sum of the f star at the point, okay? So the important bit to remember here, I'm introducing the expectation of my estimator, which is something I don't have in practice, but it's kind of saying, if I fix k, but you give me an infinite number of points, what kind of function do I get? I won't get that star because I fix k, but I will get something which is basically looking at the whole distribution. So it's an intermediate object, okay? And the basic idea would be, how do you think this guy is related to f hat, and how is it related to f star? We can start to think a bit how choosing k is going to affect my ability to approximate star or being close to a simple solution, okay? So remember that this is just the same with yi instead of f star, okay? So this is f hat k. So when do you think f hat k will be close to this guy? For small k or for big k?
Okay.
You say?
Big K.
Why?
You're averaging across.
Yeah.
So you're averaging across your samples.
Oh, so let's see. Why for small k they would be different?
Because you're not averaging.
Sorry? You're not averaging. All right. So you're averaging more. Okay, that's one way to see it. You're averaging more, so hopefully it gives you a bit more stable. But this is just an average over the noise, okay? It's not over the whole training set. The points are fixed. So the basic point here is that if you let k grow, you average more. The other way around, if you take k very small, you will jump around. Whenever there is a little noise, your solution is going to change completely, okay? So in this case, my f hat, if I give you this point, this one, or this one, or this one, the solution is going to change completely, okay? Whereas if I give you the expected version, well, it's going to average out and it's going to be very stable. If I now increase k, as you say, I'm averaging out a bit more in the neighborhood. So even if I have a single point with a lot of noise, there are other points that might somewhat smooth out my prediction. So yes, averaging is basically the answer, okay? But the point here is that you can literally add and subtract this in this expression. So you basically have f star minus the expectation, and then you have the estimator minus the expectation, and this, you can prove that there is one piece missing if you do it, and because it's 0, and you get two pieces. One is the bias, and one is the variance. Variance is called variance for obvious reason, because the variance of the estimator is himself minus its expectation, squared. This is called the bias, because basically you are not allowing your method to reach the right solution, because you're fixing k, okay? If you let k change, you might be able to approximate this more, but if you fix it, then basically you introduce a gap between your potential solution and the best possible solution. Again, you can keep on going, and what you have is that all these quantities are extremely simple. I gave you the equation. They're really simple to study, and what you get is this quantity here turns out to be just proportional to the noise divided by k. And this is basically what we guessed just thinking about it. So as k increases, this basically increases. This is a bit more complicated to study analytically. Intuitively, what you can think of, you're actually averaging the right solution, okay? So you have the right solution. You have a bunch of points, and if you average a few, and if they're dense enough, it's probably going to be a good estimation of this point here. So the idea here is, I have this point, now you give me a new point here, okay? If I take k sufficiently small, I'm going to do a local averaging, and if I don't have many points, it's going to be not so good, but if I have enough points, I will get something reasonable. For sure, if I start to take k very big, I'm going to do a ginormous averaging across all possible values, which this time are noiseless, okay? These are the noiseless values. And some kind of somewhat dilute information contained in the true value functions by averaging over a lot of things. So this term is a bit harder to study, but we can guess that if you let k increase, you're going to make your prediction worse, because you're doing a global averaging of the correct value. You're literally like assigning to this one point here the mean of the whole function, okay? Noiseless. So the main point of this story is that if you look at your estimator, you compare it to the best solution, you add and subtract its expectation, and then you study analytically the terms you get, you basically get to know that minimizing the error with respect to k gives you two quantities. One is decreasing in k, and the other one is increasing. And you can prove that these are actually not bound, they're actually quality. So here I just make it into a drawing. Basically, you're going to have, if you look at the complexity of the model, in our case, k controls the complexity. The smaller is k, the more complicated is my model. Oh, I get something. And basically what you get is that the variance and the bias behave in a different way. And then you can basically choose as the value of k, the optimal value of k, the one that strikes the best balance between these two parts. On the one hand, you want to, if you're given, remember, you're given a limited, noisy amount of information, and so you want to choose as k is small enough to control the variance, but eventually you want to allow yourself to choose k increasing so that you can get the whole complexity of the model. In all the example I showed you before, if you give me an infinite amount of data, we'll just get k equal to 1. Okay, that's okay. I can just get every single point. I have each of my points will have a neighbor which is essentially being distinguishable. The problem here is really that because you have a finite amount of data, you want to strike balance between controlling the variability and the bias. So mathematically, this is one instance of the idea that you have to control the stability and the fitting of your data. And this answers the first question. Is there an optimal value? Yes. Okay, it's this guy. Now you can sit down and try to find it. And the next question is, can we compute it? And the answer is, not quite. Okay? Because you're basically introducing a lot of quantity that you won't have access to. You're producing the average of the true solution. Clearly, it's not the quantity you can have. Okay? So one way to do this is to try to find an analytic bound that holds for any possible data set. Historically, this has proven very hard to find sharp bounds. Okay? And it's constantly being suboptimal with respect to another approach, which is basically try to approximate something like this from data with some kind of data-driven procedure. Okay? And the one method which I would say is the one that 90% of people use in 95% of the problem, is cross-validation. Okay, there are many others. There are many cases, for example, in inverse problems, not so much. In some inverse problem, you might have a very good knowledge of the noise, and you might use something like L-curve or something called Morozov discrepancy principle. There are a bunch of different methods. But in machine learning, I would say, I don't know anybody who doesn't use this. Okay, I would like to know if there's anybody who uses anything else. I'm going to show you what it is. Does everybody use it because it's fantastic? No, because we are terribly ignorant and unable to choose parameter in a good way. Okay, we will see that we are very good at inventing priors and loss functions and data fit terms, and we are terrible at finding a balance between these two ideas. And cross-validation is kind of the one thing you can do. Well, I guess from a probability, yesterday we introduced the probabilistic perspective. From that perspective, cross-validation is replaced by another data-driven procedure, typically, marginalized likelihood related ideas. I guess, I don't know. Anyway, so you have two instead of one, and they still don't work that great, but it's pretty much what you can do. Okay? Yeah.
Maybe I'm missing something. Shouldn't the bias be the difference between the function and the average the estimate?
Yes, of course. Yes. Yeah. So this plus here, then the minus. Then, how long has this been going on?
The whole time.
Always. Always. What? Once was, but then it began to be like 3 out of 4. All right. So, what's cross-validation? Well, there are different flavors, but the idea is try to somewhat mimic the situation. Unfortunately, you cannot produce a ton of data like on the right. So what you're going to do is you're going to take these points, split in two, use half as if they were training, and the other half as if they were test. And so you now optimize K over the half you took out. Okay? So whatever number of points you have, you split, you use, say, a percentage for training and a percentage to choose your parameters. Now, there are immediately a bunch of questions which are, okay, this is the basic idea. You give me the data, split this for training, compute nearest neighbor for many possible K here, and then choose K that give me the best solution here, and then when you give new data, just use that K that you choose. Okay? What's the problem with this? Or do you think it's going to work or not? So most of my questions are kind of stupid, and I do because otherwise I fall asleep. If you answer quickly, we keep on going. Otherwise, I don't know if you're all asleep.
Well, wouldn't this be highly dependent on where you draw the line?
Right. So, basic point here is if your data set is huge, so this whole thing depends on where I drop the line. Okay? Now, if my data set is huge, you can say, well, probably it doesn't matter that much because all the data sets are going to be pretty similar between themselves. But we've seen before that if this guy is just 20 points, if I drop the line in different points, they're going to be very different. We've got completely different solutions, okay? And so the basic idea is if you have big data kind of stuff, where you have tons of points, maybe this is just fine, okay? You can just drop one line. If it's not, well, then typically you want to repeat this, okay? The idea is that you're going to do it once, then you drop a line a different way, then another different way, another different way, another different way. You average out, and then you take that as your estimate of the future error in the attempt to reduce the variance, okay? And the first one where you split just one is basically the holdout cross-validation. And the rule of thumb is if you have a lot of data, just use that. If you don't have that many data, just split more than once, and this is called K-fold or V-fold cross-validation. The extreme case is when you have so few points that basically you're going to take 1 point out at a time, okay? I'm not really sure if it's anymore true, but until like 5 years ago, there were a lot of biology problem graph, for example, microarray data, terrible diseases where you have few samples and then you have like 50,000 features and 20 people, okay? That's kind of good because you don't have this kind of data much, but at that point you don't really know how to split. So what you can do is you take one person out, train, pull it back in, take another person out, keep on going, okay? And what you clearly see is that in general you pay a price for your variance reduction in terms of computation. Really, if you just split one, you have to compute for each k one solution, but then you're done. If you repeat many times, you have to put many solutions for k here, many solutions for k here, many solutions for k here. And if you take just one out, it might be too much, okay? So in some sense, there is really a trade-off between big data sets and small data sets.
So is there any like analysis of what n to choose in general?
Oh, what, sorry?
Sorry, how much of your data to hold out?
So, what I know is the following. So for the holdout, so if you just split once, and so the only question is, I just draw the line once, but I don't want to know where. Basically, anything which is not crazy works, and you can provably show that is as good as if you knew the bias variance trade-off. Okay? So basically, anything, I think the rule is basically anything polynomial. It's like anything which is proportional to number of points. So half, 70% is, for example, choices that do work, and that's kind of what you would do in practice. 70, 80% is kind of what you would do in practice, and you can prove that it works. Okay? The question which I believe there are some results, and I've been always postponing looking carefully into it, is analysis where they tell you what is the effect, how much you reduce the variance by choosing many splits, okay, and choosing different size. And this is actually something, I think I do have pointers, but I'm not sure actually. It's definitely, so cross-validation is kind of this crazy thing where most people use it, and most people have no idea of the theoretical properties. I'm epsilon better because I recently studied the holdout version, but the k-fold, I'm still a bunch of people lazy looking at the results. There are a few results. There are a few more than you think. To some extent, the laziness is justified by the fact that none of these methods is working great. Okay, so even if you knew the theory, it's unclear whether this is going to inform you in a better way of using. In the end of the day, you have 2, 3 choices, and you cannot use that. I think the big problem is really to come up with substantially new ways of doing it and try them a different way. Okay? It's funny enough because sometimes I say this can be a very long story, very short. It's very long because basically, I would say, substantial amount of theoretical statistics and mathematical statistics is dealing with this problem. Okay? Find adaptive choices that work as well as the bias variance trade-off, but just based on the data. On the other hand, the story is very short because in machine learning, it's cross-validation. Okay? And so to some extent, there is this big gap. It's one of the biggest gaps between theory and practice, I would say.
Sorry, also one more question.
Yeah.
Do the general points that you're making hold for non-least squares?
Mm-hmm. Yeah, so basically, in this stuff here, I chose least squares, I chose this method, and I chose everything because this computation, aside from this you need to be a bit fancier to compute. So here you just intuitively convince yourself that it is actually increasing with k. But everything else, you can literally do, as an exercise. So that's why I choose it. In general, if you choose, you can definitely choose other models, choose other loss functions. You can keep on going. The main difference is you might not be able to get qualities. You might get inequalities, and then immediately you're into the game of finding how well your upper bound is matching a lower bound and stuff like that. How tight is your bound? But everything I said, it holds for general model of the data, classification or regression of any kind, any loss function. But beyond that, it holds for density estimation. It holds for 90% of the estimation problems that I know. This is, I want to show it to you because even if you've seen it before, this is like a very important pillar of pretty much everything you do. You want to know that it exists an optimal value, and you want to know that, at least in practice, cross-validation is one way of doing it. And there is a big question of how to do it in different ways. Okay? And this was really the point of this first section of the class, okay? Yeah.
Is it okay to use a different loss function for fitting the model and then choosing your hyperparameters? Do people do that?
The second question is easier. Yes, I do it all the time.
Okay.
So, for example, one question nobody asked, but the question which is asked quite often is, why would you use least squares for classification, for example? Turns out that there are tons of reasons to do it. Okay. That probably takes me a bit more than a few seconds to explain it. But typically what to do, for example, I use least squares, the one I'm going to show you in a second, all the time for classification. But typically I choose the parameter choosing another loss function, like just counting errors. Why? Because typically works better. The hard part for which you really want to have a convex and nice loss function is when you have to do the training, because you want to try to get convex optimization problem or easy optimization problem from a computational point of view. But when you go and try the model, you just have to compute it. So unless it's insane, you just have to compute it and check is the best value. So you don't care that much. So you typically want to use the best when you can. Okay. Do we have any analysis of this? I'm not sure. I'm actually kind of sure it's not anything reasonable. But you do it all the time. In some sense, especially in classification, the choice of the loss is not that much because it's the best possible thing you can do, but it's the one you're forced to do because the one you would like to use is non-convex. So you just go to one that you can actually solve in practice. So as soon as you can go back to the real one, you do it. And so this kind of ends the first part. And as I was saying, I just want to show you an instance, the simplest algorithm to show you this trade-off between stability and fitting, and try to give you a glimpse of the theory that tells you how to resolve this trade-off in theory and actually how you can do it in practice. And at this point, you can wonder, if you tell me that they're simple to study, if you tell me they work reasonably well in some situation, shall we just stop here and go home? And somewhat the answer, one possible answer comes just from looking at a simple exercise, which is kind of boring to read, but simple. Take a cube, okay? The edge of the cube is 1, so the whole volume is 1. Now the question is, suppose that I want to put a cube inside. Don't admire my amazing drawing. So I want to know how big it has to be this cube to occupy 1% of the volume of the big cube. Okay, so the big cube is edge 1, so the volume is 1. I want to have the volume of this to be 1%. And so I'm asking you how big this has to be. The mathematical problem. What do you have to do?
Cubic root.
Right, you just have to take a p fruit, or whatever it is, okay? So let's plot it. If your dimension, so this P1, 2, 3, 4 is the actual dimension of the space, okay? So if the space is 2-dimensional, you take the square root. If it's 3-dimensional, you take the third root, and so on and so forth. So what do you see? If you take, say, P equals 10, how big has to be the edge of the little cube to occupy 1% of the volume of the big cube? How do you read it out? Well, you go here, you check the fraction of the volume you want, then you go up, and you check what is the edge, okay? And you see that basically in 10 dimension, not exactly a huge dimension for us, the small cube, you know, our perception in low dimension would be that it's this big, okay? And if you go to 100, the small cube is as big as the big cube, okay? More or less. It will be 0.999 something. Did you ever see this before? So understanding what's happening in high dimension is a mess, okay? And stuff like this is not meant to just give you a perfect picture of what's going on, but just to warn you, okay? When you go to high dimension, stuff that you typically take for granted, like being close or distances, are completely different, okay? And so you move in a space where, in some sense, everything is close and everything is far away, okay? And the very notion of locality starts to be tricky. And if you just take locality for granted, you might get in trouble. This does not mean the Knearest Neighbor is not going to work. If you can look at very nearby points, it should work. But if you can make the distance small enough, whatever that means, it might work. But in general, small enough is a tricky concept, okay? And the other thing is that in general, the space is in some sense very empty, okay? When you look at the number of points, if you have 20 points, is it a lot or a little? Well, it depends on the dimension in some sense. If my space is very small, if the one dimension, like here, maybe some 20, 50 points can be a reasonable amount. I don't know. But for sure, if I go and put myself in 10,000 dimensions, 50 points are going to be very few. And all this kind of stuff is going to have a dramatic effect. And the point of local methods is that not only the distance become a tricky concept, but in some sense that I never have enough points to do the local voting. Okay? So oftentimes what I want to do is I want to move from local method to something global, so that the prediction here is going to exploit to some extent the presence of other points. I'm going to assume that the function here has some regularity, so that if you know the value here, this actually might be able to inform the value somewhere else. Exactly because, as we said yesterday, we're going to make smoothness assumption. And then all of a sudden, to make the prediction here, I'm not going to look only at these 5 points here. I might be able to look at the whole 50 points here. And then I borrow strength from faraway points. And so from local, I want to go global to try to beat the terrible curse of dimensionality. Okay? This idea that in high dimensions, distance acts in a weird way and the space is mostly empty. And that's why we're going to move and look at something more complicated from an algorithmic point of view. The first part is going to be basically the version for dummy of what Maha showed you yesterday. So I'm just going to stick to matrices and just give you the simplest version. And then the interesting part will be more when I replace the simplest model with slightly more complicated model. Good news is all the computation will be the simplest you can get, but the models are actually getting kind of interesting. You can actually kind of get state-of-the-art machine learning algorithm with 3 lines of code. So the general gist here is going global and try to impose some smoothness. And this is going to be our main character. So I give you the data as before. For the time being and for a little while, we're going to assume that we look at functions. They're actually linear. Okay? And then we're going to take this kind of minimization. We're going to discuss it quite a bit. Basically, we saw already this yesterday. Just as a historical remark, this kind of idea kind of came out around the same time. And I thought yesterday I was looking a bit, it's kind of funny that, so this is usually called Tikhonov regularization. Looks like this guy Phillips, and this is the best picture you can find on the web. Tikhonov is everywhere. Phillips didn't make it. And they kind of did exactly the same idea around the same time. Okay? In fact, some people do call it Tikhonov-Phillips. I was checking the paper. They're very similar. In some sense, Tikhonov already thought, as other related mathematical results, was giving a bit more context. But in terms of this method, Phillips kind of had the same idea. And for the record, statistician also had the same idea. They actually had this idea. Okay? Literally, this one I'm showing here. As Maha showed you yesterday, Tikhonov set everything up in a much more general or theoretical framework. Okay? Statisticians were more concerned with this problem. They call it ridge regression. Okay? But this is one of the first start in the name game in machine learning, where we have 15 different things invented 20 different times, and there are a lot of names. At some point, you have to go back and some theory to show that they're all the same. The other thing I was reading yesterday is quote from Legendre, who was a big fan of Lee squares. I am a big fan of Lee squares, mostly because they're very nice analytically to study, and they work pretty well, where I have very few instances where they are destroyed by something else. We see, I think that Maha yesterday commented that in some sense, and it's true, and this is an extra parenthesis here, Lee squares are less robust, which is definitely true, but when you regularize, you can recover a lot of the non-robustness in practice. And the key is just that it becomes much more painful to choose the parameter. Okay, we're going to comment on that a bit. To some extent, oftentimes in practice, Lee squares are not as bad as they could be, given that they are so, they have the square here that makes you pay for big errors so much. So apparently, Legendre came up with the idea of Lee squares in 1805, and a few years later, Gauss. I thought that Gauss came up. I always thought that Gauss came up with this, but yesterday I was reading. It looks like Legendre came out with this in 1805, and Gauss, which from the record doesn't seem to be a particularly shy guy, came out with a few years later, basically saying that he already had it in 1795. And then there was a big fight and blah blah. But it looks like historians right now believe that perhaps Gauss was not lying, and it's really the one that invented it before. I like the quote anyway, so here it's a good boy Legendre. So what is this doing? Well, for the time being, that's what we're going to do. Okay, we're going to take our points as before, and we're going to draw a straight line. Okay, and we're not going to look at this because it's going to be interesting from a statistical point of view, but because it's going to be everything we need to know from a computational point of view. Once we got the computation right for this, everything else will be very easy, okay? One word of warning. I'll often draw this line. This line is not W transpose X, okay? This is W transpose X equal to 0. This is my attempt to draw W transpose X. And the Italian version of this is that the data lie here, and then you have the plane cutting through, and this is W transpose X, and this is just the 0 level, okay? So if you do classification, you compute W, you apply to a point, and then you have to take the sign. If it's positive, you say +1, and if it's negative, you say -1. Okay? This is a very simple remark, but I remember the first time I saw it, I would often forget that this one line here is not W transpose X, okay? I would just, and if you make that mistake, then it becomes kind of complicated to recover, you get confused. Okay, so just keep that in mind. So what we're going to ask at the beginning is, we're just going to, remember real quick, what are the computation underlying this kind of methods, okay? And they're very simple. And next, we're going to look a bit into statistics, but a lot of it was basically covered by Tommy and Maha yesterday, so I'm not going to indulge in that too much. So, computations. This is why this course is nice. If you wish, just write this in vector notation. Remember, xn is my data matrix, is n number of points, p number of dimensions, or t number of dimensions, and this is my vector of labels. Just rewrite this in this vector notation so that perhaps even more easily you can check that this is just the gradient of this term, and this is the gradient of the second term up to a lambda. And so now if you just set the gradient equal to 0, you get the normal equation associated to the above problem. Okay? Again, take a message here. If you've seen this before, sorry. If you've not seen it, you just have to take a gradient, set it equal to 0, and that's everything you have to do. Okay? And then what you have to do is to solve this linear system. And we want to look at this linear system a little bit. So, again, so this is going to be a sketch of what you saw yesterday. What is this thing doing from a numeric point of view and from a statistical point of view? Well, the simplest case to understand it is basically look at the linear system. Let's just say it's square. Let's just say it's easy, okay? And then what you do, if you really want to make it simple, is you just take to be a diagonal matrix, okay? It's not quite the identity. You put something at the diagonal. These are numbers, and they go to 0. And then solving this problem, you have to invert. But what's the inverse of a diagonal matrix?
1 over the diagonal.
It's just 1 over the diagonal, okay? And now you immediately see what's the problem we already saw yesterday. If the eigenvalue is small, even in this simple case, everything explodes, okay? A little perturbation here, a little perturbation here can make everything change. So what is Tikhonov in this case? Well, Tikhonov basically tells you, okay, do this, but add a lambda. If this is big, lambda will not do much. But if this is small, lambda is going to kick in and make this stable, and nothing is going to explode, okay? And this one diagonal case is basically giving you the whole picture of what you're doing. You're basically considering a filtering. You can view this as a kind of filtering. As Maha said yesterday, you can view this as modes, if you wish, Fourier modes. And so this would be something like low frequency, and this would be something like high frequency. And you can view this as a low-pass filter, if you want, from a filtering perspective. If you like low frequency and you want to let them be, but if your frequency are too high and they're going to give you potentially oscillatory behavior, you want to kill them, okay? And this is one way of doing it. And in fact, if you look at this, you can probably think another 5 ways of doing it, just basically defining filters, okay? And indeed, this is one way to build learning algorithm, but this is by far the simplest, okay? We probably won't have many times where we have diagonal matrices, but if they're not diagonal, you can, in this case, and in our case, you can just take, in fact, the eigendecomposition of the matrix. And basically the same story holds, just you have to squeeze the inverse, this diagonal matrix of eigenvalues, in between the V and V transpose, which are the eigenvector and their transpose. Okay? And this is exactly what the way we're gonna think of this. So notice that this matrix here, because the way I built it is in fact square, and how big it is. You have endpoints, and you have, say, D variables. How big is that? This is D times D. Okay? And how big is this? D times 1. So, the basic idea here is, from a numerical point of view, I'm stabilizing the problem. And to some extent, this is for the same reason we are stabilizing the statistical problem. The sampling of the y or the perturbation over the x are not going to affect my problem because I'm actually making the problem stable, okay, numerically. And this is one window over this interesting interaction between stability and generalization. Tommy told you about related ideas in a much more general setting. But this is kind of an instance where you really see the interplay between statistics and computations. And it might be worth mentioning that right now, because we have these huge data sets, where you typically cannot just assume that you can have perfect computations, this idea that you might want trade-off stability of your computation with model accuracy is becoming like one big trend. And this idea that you basically have to make estimation under computational budgets, computation budgets, memory budgets. So you really want to know how this all aspects interact with each other is one of the most active and exciting fields, I think, both from a practical and a theoretical point of view in machine learning. And to me, this is like the simplest instance of this interaction between computation and statistical model. One thing I don't want to tell you about, but I want to tell you it exists, is a whole different point of view that I personally just discovered in the last couple of years, but Stein actually discovered in '56. And it's a whole slightly different point of view on why you do regularization, which is not really taken an inverse problem point of view, but is definitely taken a stability, the interplay between stability and estimation point of view. Here I'm just going to tell you the keywords, and the keywords are the idea of so-called admissible estimators in statistics, so-called Stein effect, given by the name of a person who first figured it out, and then this idea of shrinkage. That's how a lot of statisticians will call something like this. They will call it shrinkage, and the justification will not be numerical stability, but in fact would be the result by Stein. Okay? So I hope I make you curious enough. Plotting the solution for least squares is not the most exciting thing ever. But let's do it. What do you expect? Expect a straight line. Very straight. Okay. You can check that probably if we can check here that it's still lambda does what lambda is supposed to do, especially if I take fewer points and let's say noise hard. If I make lambda this big, let's see if I can move it around a bit. I get this guy. So I'm just changing, I just put the linear least squares and I'm just changing lambda a little bit. And what you expect, if this lambda is small, it should be a bit more unstable. If lambda is big, it's a bit less unstable. And let's see if it's true. Take another data set. Not much. In this case, you can run it a few times. Basically here, this is the kind of stuff that will encourage you. I don't know how much you've seen this kind of stuff, so if this is your bread and butter, probably you want to do something complicated, but if you've not seen this before, if you just play around with this a bit, you got at least an intuition of how things would change. Okay? Instead of doing twice as I'm doing it now, you can basically check, if you want to force this to move around, you will probably have to take lambda very small, take the number of points very small, increase the number of points, so you get somewhat instability popping out easier, okay? And here I'll stop because I get then I get all excited and I start playing games. But that's kind of what this is about, okay? Okay, so that's about it. In the next couple of slides, what I want to show is a substantial complication of this. So first of all, is this clear to everybody? I'm going to build on this for quite a while now. So does this make sense to everybody, both from a computation and modeling perspective? Because this is a great moment to stop. I take this as either breakfast digest or it's perfect. So, we basically want to understand a couple of things. One is question related to the computational complexity of the problem and how to try to make it as best we can. And the other one is really, and it turns out that this question is related to this other question, which is, why shall we look at linear decision rule? Okay, maybe I want to look something like this. Okay, as I told you, from a good news would be that from a computational point of view, we won't need to learn anything else, but we can just play around and be able to actually look at stuff like this. Okay? How do you do that? Well, the simplest way is this. Okay? Somewhat rich conceptually and very simple mathematics. You take a vector x. This is x1, x2, x3, f2, xb component. Okay? It's an image and it's pixels. But then instead of using just pixels, what you do is that you define a bunch of measurements. Okay? Or if you want functions that take the image, the whole image maybe, and return a number. Okay? I have one function, another function. For example, I don't know, I can take an image and take a patch and take the average. Okay? Then I take another random image and I take another patch and I take another average. And then I take the same two images and the same two patches and average, but I do it in another image. And I define this dictionary of measurements. Okay? You can think of them as features. That's how they're sometimes called. You have the whole image, and then you extract these numbers. Okay? So for now, we're not going to discuss how. In fact, I'm never going to discuss how. But I'm going to discuss what you do with that. Okay? And what you do is very simple. Notice that you can just call this x tilde if you want. Okay? It's just a name of another representation of x. Okay? That emphasizes the fact that it's just another vector. Instead of x is another one, defined by other measurements. But it looks very similar conceptually. If you now write W transpose x, okay, notice that this vector might be d-dimensional. Typically, you want this p to be much bigger. Okay? And you'll see in a second why. And if you write down the curve, you can actually expand the equation this way, and then you see somewhat why you want to call it dictionary. Okay? Because if you look at it from that perspective, what you see is that basically you can think of this in the simplest case as a basis. Okay? And this is just a linear combination over a basis. So you're choosing a basis for this function space, and then you're just trying to find the best expansion for this basis. Okay? This is the analytic perspective. The other perspective is, and this is what a lot of mathematicians would like, the other perspective is actually more geometrical, and is basically the following, and is the one that makes the fortune of supervector machine. And it's the idea that you basically do the following. You actually map the data, and you work linearly here. And so from a geometric point of view, you can view it as follows. Suppose that this is your data set, okay? Clearly not linearly separable. But now this is x1, x2, map it into three variables, z1, z2, z3. This would be my x1, x2, z3 tilde, okay? Defined this way by the first two coordinates, okay? So I take x1, and I take z squared. I take x2, and I take z squared. And then I take x1 times x2 squared root. Okay? I take each point, x1, x2, and I map it in a corresponding point defined by these three coordinates. Then I look for a linear solution. So this would be z1, z2, z3, or whatever you want to call it. Then I look for a linear solution in this new space, here. Okay? And here I recycle everything I knew before. This is just the same as before. But then I can go back. And what is linear here, this linear separation here, is no longer linear here. And this functional equation clearly show it to you. If you put, instead of phi j, these numbers, what do you get? Okay, so instead of phi j x, just put this. Okay, you put it here, so you get x1 squared wj, x2 squared wj, x1 times x2 wj. What is that function? Yeah, it's polynomial. It's just a polynomial of degree 2, okay? And remember, this is not this function. It's just the zero level set. How does this function look like? That's what you're saying. It's like a parabola coming out of here, okay? There's something that goes down, it's positive here, and it goes down there, okay? So
sorry, I got a question. Then do you have to know how to transform your data into this thing that's then linearly separable? And so it kind of seems like a chicken and the egg problem.
It is and it is not. So it is because you would like to be able to have a principal way of doing it. So I'm hiding behind how you choose this, okay? But this is a good moment to have this discussion. Whenever you have to choose stuff like this, you would love to have a theory that tells you how to do it, or even better, how to learn this kind of stuff, okay? And a lot of what you will see, I don't know if Tom is going to talk about, a lot of ideas, for example, that bring idea from neuroscience into machine learning are about how you actually build stuff like this. A lot of the deep learning ideas that are around these days are basically related to how you do this, okay? But I would say, up to, say, 5 years ago, right now it's an exciting moment because we're exactly thinking about this question. We're thinking of a question, okay, how you choose this. I would say until 5 years ago, there were two main trends, okay? One was, this is not a theoretical problem, but this is just an engineering problem. So what I'm going to do is I just give you a different name for the same thing I did before. So this was the name for the raw data, the pixels, and this is just another name. And how do I get there? I go to an expert and I say, when you recognize a face, what are the things that you're going to look at? And I say, maybe I'm going to look for a novel, and then I'm going to look for something else. And so you just try to build this by hand, okay? And it becomes basically handcrafting of interesting information. For example, in the case of text, you might do word count for a given dictionary and stuff like this. And the literature on this is ginormous, and just putting some order is very complicated. The other point of view is really coming from this perspective, okay? And this is another answer to the question. So basically what you do here is that you take a dictionary of nonlinear functions and you try to make it as large and rich as possible so that no matter what this function is, this might make it. So we were, remember the other day discussing, for example, results about neural networks. You can prove that an appropriate choice, that neural networks do correspond to some kind of choice of a model like this, and they are so-called universal estimator, meaning that you can approximate everything, okay? And you can take splines, and they will also have properties like this. And you can prove that if you will see in a second, many other choices of phi-j, you can actually approximate everything. You don't know how fast how you will do it, but you can. The main point is that you might need t to be very large, possibly infinity, okay? So to some extent, the simple answer to the question is, choosing the phi-j is a big problem. The typical attitude is, I'm going to just throw a lot of phi-j to the problem. Okay, I'm going to make this p ginormous, and hopefully I'm going to let the algorithm be able to handle this high dimensionality and somewhat extract the kind of information which is useful for the problem. And so, for example, you can say I take any possible features in dictionary I have and I just shove them together, and then I see this gives me something to do. Okay. So typically, the idea is that you really go in this direction where you first explode the number of dimensions, so you really map your data in very, very high dimensions, and then you let the supervised learning step somewhat project back in a reasonably sized model. Okay, so the main point here is to move away from linear models into nonlinear models. Basically, you have simplest way is to look at dictionaries, and you have these two different perspectives. The first one is more geometric, where you say, okay, I take the data, I map them into a new space, I look at the linear model, and then this model will no longer be linear in the original space, okay? And then the other perspective, which is completely equivalent, is I take a set of atoms or dictionary elements, and I take linear combination of these dictionary elements, and this is how I define my function, okay? These two things are completely equivalent. What about the computational? Well, in some sense, the answer is here. If you just take this t to be finite, it's just nothing. You're just changing the name. You have to spot the difference here. The difference here is just that there's a little tilde here, okay? But everything else is the same. Of course, the dimensions are not the same. How big is this matrix? We say it was d by d. If now I map into a p-dimensional space, it would be p by p. If my data were two-dimensional, as they are, for example, in the stuff I'm showing you now, if I now map them into a very high dimensional space, it might go from 2 dimensions to say 2,000 dimensions, even more. Okay, so you might the price you pay to get a more flexible statistical model, the potential degrees of freedom, the memory requirements to remodel become much harder. Okay, and this should up if you want in computational complexity problem. So, do you know what is the complexity, for example, of forming this vector? How many of you know what's the price of computing the inner product between two vectors? If the price of computing inner product between two numbers. You know? No, because I prepared this one slide, I can show it to you. I can just skip it.
Isn't it like unsolved?
I'm just thinking of I'm just thinking of the simple stylized equation where you're basically saying I have two vectors and I have to multiply them. I have to do p operations. They're just multiplication. I'm assuming I have infinite. I'm not talking about computational method. I'm just thinking of a simplified equation where you have infinite precision in your computation. You just multiply two numbers. This costs 1, and you just have to count the number of operations you have to do in this sense. Okay, makes sense. So in this sense, this is just a quick summary. If you have vectors of length p and you multiply, this costs you p. If you have a matrix times the vector, you have to do this n times. So it's np, matrix np squared. And the inverse of the matrix also is not exactly, but at least in this case is roughly speaking n cubed. Okay, this is not somebody from Complex would enter here called Yorify, but this is kind of Google thumb way of thinking to just compute to have an idea of the complexity of the method we're looking at. And this is kind of what you know. Okay, so these are the two ones that are most important for us. Okay. And the basic idea really is to think we have two vectors, count the number of operations, that's how we think of complexity. Okay? And so what is the complexity of this? Well, the main complexity is actually building this matrix. Okay? This matrix is n by p. I take this transpose, I have to do a p by p matrix. And this is going to cost me p squared n. Okay? And I'm thinking of a situation where n is big. Okay, I have many points and not so many dimensions, and so this is the leading term. If p is much larger than n, then this would be the leading term. Okay? Does it make sense? So this is the price to build this matrix, and this is roughly speaking the price of some solver to invert this matrix or find a solution to this problem. Okay? Typically, inverting this matrix is not a good idea. You want to do less than that. You just want to solve this problem. And the classical way of doing it in this case, because of this matrix is square, positive, definite, and symmetric, something like Cholesky composition is typically the way to go. And that's what the backslash command in MATLAB would do for you. Now, one question here is, we just said, does it make sense? Okay? These are the complexity we get for this kind of problem. Now, one hope we might get is the following. Can we do anything better if p is much, much larger than n? Because we kind of pointed at that situation to be the interesting one. Because I don't know what kind of model I want, and I just want to get a very rich model. Okay? So can I get anything better than this when p is much larger than n? Okay? What do you think? So you have to do a one-line calculation, which is very simple. And again, also this is just a simple exercise. Let's just see what I did. So x transpose, xn, and here there is an x transpose. I want to take this x transpose, move it in front of everything. And the rule is that you can do it, but you have to switch the order of these guys inside. Okay? So if you just write the spectral decomposition, the singular value decomposition of this, it's immediate to see this. Okay? It's literally like just write this as use the SVD for the matrix xn, write this, and it's done. Okay? So believe me, and try to do it as a little exercise just to remember what the SVD is. Why do we care about this? Because this is nice. Because look, W, okay, that used to be X transpose here, blah, blah, blah. Now I can write it like this. Because I can write it like this, is now X transpose of this quantity, but this quantity is how big? How big is this matrix? This was D by D, or P by P, but this is just N by N, okay? And so this vector here, and when I apply it to this N by 1, this just become an N-dimensional vector, okay? But then I can write this, if I just write this matrix vector multiplication explicitly, I have this expression, forget about the transpose there, but the point is that each W is a linear combination of the points in the training set weighted with respect to N coefficients, okay? But then immediately we can check what's the new computational price. The computational price now is the one for solve whatever is written. But what's the cost of this? So building this matrix is P square N, okay? And then inverting it is PQ. This is N by N, and to get it, I have to squeeze an N by P and a P by N matrix. What's the price? It's not this, but it is just N square P, okay? So P just enters linearly into the game. Then I have to do NQ to invert it. And then I still have to do another multiplication, but it's just a multiplication. It's not going to become square in P. And so what I have is that from this complexity, we go to this complexity. Okay? So as you hoped, when the number of points is much smaller than the size of the dictionary, the size of representation you get, is actually, you can just play it around and do this. Okay? The situation right now, unfortunately, is the one which there are actually start to be some specific problems where this is huge and this is huge, okay? And so none of this trick will work. We have to do something better than this. And in some sense, the other big trend right now, because of this new ginormous data sets we have at disposal, is to find an approximate way to kill this complexity, okay? Try to be linear, okay, in both P and N, or perhaps even sublinear in some restricted class of problems, okay? But this is somewhat, again, this is much as what I think you need to know, and then you can make it more complicated. And relatively simple methods can be actually built on top of this kind of stuff. For example, there is a recent work that shows that if you have a huge problem, you can actually split it in pieces, solve this for each problem separately, and then just average out. And as long as you choose the parameter for each piece, looking at the performance of the aggregated solution, this actually works pretty well. Okay? You split, you take the average of what you get in the end, but to tune the parameter, you don't look at each individual split, but you just look at the aggregate solution. And this can be turned from a statistical point of view, because of the independence of the split, actually works pretty well. So, and this is just one possible way, and there are a bunch of others. The one that I actually like is the one that go a bit into the detail of how you compute this, and basically show that in fact you can use first order methods like conjugate gradient, gradient descent, accelerated gradient descent, and a bunch of others. And in those cases, in fact, you can do something cool, which is put lambda equal to 0 and just use the iteration itself to regularize. Okay? This is called early stopping. You just a completely different point of view on the way you regularize. This is something I think is cool and can discuss it offline with you. But anyway, so this is the basic idea, and this is like a building blocks for a lot of different solutions. So the cool thing is that along the way of doing this, we actually discovered something else. W is written this way, okay? But oftentimes we don't care about W. All we care about is W, X transpose W, which is actually prediction, okay? So because W is just this, X transpose W, our Fx, is just this quantity, okay? And now this is really a diminishing slide, but in some sense, to compute this quantity, as long as you can compute this inner product, in some sense, you can replace this with infinite dimensional vector. So the only places, if you look at everything here, this quantity is n-dimensional, and here you just have to compute the inner product and sums over n points. So if you have a way to compute efficiently this inner product, you can actually move away from finite dimensional dictionary, potentially looking at infinite dimensional dictionary. Okay? And this is somewhat what people implicitly, again, so suppose for a second that you have a way to compute something like this, okay? And then basically replace this expression. I just gave the name KNN, okay? Kn is just this matrix here, which is just based on replacing xxi with kxxi. So what is this k? Well, for example, it could be any of these guys, okay? If the simplest choice is just the one we discussed for 40 minutes, and it's this guy, okay? But another choice is, for example, this guy. So you take x transpose plus 1. Do you see anything at all? 0. Anyway, so you take x transpose x plus 1 and you take the e power, okay? And the last example, which is the one which is really more powerful, each of these you can prove that is in fact equivalent to choosing a phi j, as I showed you before, which is in fact finite dimensional. This is trivial. This is a bit more complicated, but you can do it. The last example is the one where instead of just taking here the inner product, I actually replace it with this Gaussian. Okay? So my function becomes a combination of Gaussians centered at the training set points. And one can prove that in this case, there is not a finite dimensional characterization of the space. This is not a finite dictionary. It is in fact in general an infinite dictionary. The simplest case you can think about, if you're in one dimension, you can basically show that this is essentially the, okay? And also, I kind of abused everywhere. I didn't point out everything from the point of view, which is Gaussian processes, which is another big class of stochastic processes that can be used in a lot of modeling problems. And there is a beautiful connection with that is an integral equation, which is completely invisible here, sampling theorem, inverse problems. I didn't do it just because, again, I'm trying just to give you algorithms and the way to use them, okay? And I just want to try to stay away from too much math and theory. Other stuff that I didn't tell you at all is a lot, which is actually more important, what I'm trying to achieve today, is a lot of different kind of generalization of this. For example, square laws. Why square laws? Something else? Sure, go on. You take so-called logistical function, you get logistic regression and kernel logistic regression. You take so-called hinge loss or epsilon sensitivity loss, you get supervector machines. All of this will be kind of, once you know this, then you just have to add a little bit, and you know all these other algorithms, okay? Another thing you could do is to say, why binary labels or real valued functions? Can I learn vector valued functions? Sure. It's much harder. We don't have a very good idea of how to build function spaces, but you can do that, okay? And I didn't tell you how, but you can use to multi-output function, and for example, to go from binary classification to multi-category classification. And it's going to be a minor twist, again, at least the basic solution will be a minor twist over the solution I just told you now. From a practical perspective, the thing you should remember is basically that now what you can do is you can build your own dictionary, but you can also use these kernels that do give you a bunch of different solutions. So, what is this? No? So let's close it. Let me just start 1 second. Oh, wow. We draw a lot of stuff. Oh. So this is linear range test. Okay. Now let's see what happens if I switch from this to the Gaussian kernel. This game I'm playing is kind of the one game that all of machine learning people spend most of their time doing. They have a problem, they build this kind of algorithm, they take the linear kernel first, kind of not so good, but in high dimensions they might do well. But let's try the Gaussian kernel and let's play a bit with the sigma. this what's going on. That's exactly what I'm doing. So let's try. Take the Gaussian kernel, I take the regularization parameter. This is the lambda. This is the sigma width. Train it. Doesn't break, so I'm happy. Test, and pretty cool. Okay. Of course, all these parameters that I'm throwing there, I could do and I should do a cross-validation. Okay, this is just to show you what you get. This is kind of the general idea. This is what you get with these squares, with linear kernel, and this is what you get with the Gaussian kernel. How you should think about this? Remember, this is not f of x. This is f of x equals 0. How does f of x look like? It looks like this. Sit on here and put a Gaussian of width 0.04, whatever I chose. Okay? And do it on every single point. Then you have to choose the height of the Gaussian and the sign. If it's positive, it comes out. If it's negative, it goes up. Then you connect all the tip of these mountains, and you get something up here and something down there. Okay? Then you look at the levels at 0, and this is what you get. And this, I was lucky, and it looks like I chose some sigma, which is kind of reasonable. Let's see what happens if I try to make it much smaller. Nothing. It breaks. I'm really going a bit random here because I don't know what is the numerical person. I didn't look at the eigenvalues. I don't know what's going on. Okay, so I just changed sigma. Okay, and I make it very small, but very small because I get, there is a Gaussian here. Okay, and basically I can get to stuff like this. And what you see is that you start to see that this is really probably a mountain and a valley, and it goes up again. And for some reason, it wants to go up here again. Okay, so this is really something going up and down. I wanted to try to show to you that if I try to make this smaller, that's right. Okay, so what I want to show to you is that if you start to play around a bit, and if you play with sigma, what you can do is basically really put a bunch of Gaussians. I didn't prepare any setting. I'm just playing live on this. But you could literally go and start to look at this solution. This is really clear. There is one Gaussian here, one Gaussian here, and one Gaussian here, pretty much. Okay, and so you can circle out points. Okay, these are small. They don't see each other. These start to behave very similar to a local method. Okay, you basically just put the Gaussian around each point. And so you get, by using the Gaussian kernel, you can get this whole range of complexity. Does it make sense? If you go on the other side, and you put here, let's try one. So if you go on the other side, so if you do regularize, and you just be, but the point I want to make, show it to you, is that the more you make the Gaussian big and the more you regularize, the more, this is exactly the same data set as before, but if I can keep on going, in the end, this is going to behave essentially like the linear kernel. I make Gaussian so big that essentially I'm going to have a function which is very smooth, okay? Now, these algorithms are really the workhorse of most of applications, okay? Might not be least squares, might be super vector machines, might be logistic regression, but this is what's going on, okay? A lot of state-of-the-art solutions for supervised learning are based on these methods, okay? Either for intelligent system or just make prediction of all kinds of practical problems. And we worked for like an hour on this, and we learned that we can play around and we can switch from one complexity to another complexity. And by essentially using the same code and just changing the per-processing, choosing different dictionaries or choosing different kernels, we can actually get a whole range of different kind of models, going from linear to something more complicated. And so we actually can start to ask, what else do we need, okay, to solve supervised learning problems? It's a pretty big toolkit box already. But before asking what else we need, I think it's good to take a break. We die. Think of what else you want to see.